Oh, Henry just oh, Henry, you just noticed that everybody saw marks on the seminar webpage?
I didn't notice that.
Oh, I see. It's been there ever since the seminar resumed.
Yeah, I missed it. I don't know. Maybe I'm just so used to it, I don't see it anymore.
So, Renata, you're going to be sharing your screen, or what will be the
Yes,
setup?
I am trying this setup with my phone camera, and I'm going to be writing down on my tablet. So
Okay.
I don't know. Let's see how this works. I don't know if the video is necessary because I'll be looking down the entire time, but I can try. Yeah, okay, so I can share the screen. Oh, just a second.
Yeah, of course, whenever you're ready. So then.
Yeah.
No rush. So we
can you see?
Not. Oh yeah, I can see it now. Yeah, sure.
Okay.
Yeah, cool.
Then this is what I'm going to be doing. Okay, so I'll write the title in the meantime. So I'm going to be talking about virtual classes, or oh, I'm sorry, this is not working.
Yeah, take your time, set it up, and then we'll start whenever whenever you're ready. Yeah.
I tried this before to make sure it worked. No, of course it doesn't.
It's an informal seminar. No pressure.
Okay. Yeah, I don't know what it is. It's not recognizing the smart pen. Okay. So I'm going to be talking about a virtual class of the moduli of stable maps. With p fields. So what I plan on doing is to first give some very broad general overview and motivation to sort of motivate for, whoever hasn't seen it before, where the moduli of stable maps of p fields comes about. And yeah, this is going to be sort of a very brief overview of a very large general picture. So, but what I want to highlight is how the role that the quantum leftlet hyperplane principle plays in Gromov-Witten theory, and how stable maps with p fields are sort of an analog of that. Then I'm going to be talking, I guess, briefly, since my story is a lot about virtual fundamental classes, a little briefly about the virtual fundamental class of Gromov-Witten theory and the perfect obstruction theories. And I guess I'm going to be talking also briefly about the genus 0 story of the quantum leftlet hyperplane principle, for the point of view of how it is some functorial statement about virtual fundamental classes. And that's mostly because I find it very nice, and because I would like to understand what I've done from that point of view, though I'm not quite there yet. And then I will talk about, stable maps with p fields, and what I actually proved. And then to make it a little more concrete, I'm going to talk about some concrete aspect of the proof that I found really nice. That is, it's just a nice piece of information that I didn't know before, that I found out. And basically how a key ingredient of the proof is to find a different perfect obstruction theory on the modularly stable maps. So I'll be talking about two perfect obstruction theories. Okay. So for the broad motivation, yes, I'm sorry if this is imprecise, but I guess most people here have heard some version of Melissa's work and Melissa's talk on the subject, and there's also a great expository paper that she has with her co-authors that talks about this more in depth. But the basic motivation comes from the study of the Gromov-Witten theory on the quintic threefold. So Q, that is the vanishing locus of the Fermat quintic, or some other quintic, in P4. So is the vanishing locus of a section of O5. And the moduli space of stable maps of genus G to the quintic threefold has virtual dimension 0. So for any genus and degree. So it makes sense to do virtual counts on this, and one can define the virtual counts or Gromov-Witten invariants as integrating against this virtual class and package them in a generating series. Now, as far as I know, the question, at least in math, not in physics, is still open to compute this generating series, even though the individual numbers have been computed, can be computed for genus greater than 2. And so one of the key tools in all the computations that have been done is relating the theory of the quintic to some twisted theory on P4 or to the Gromov-Witten theory of P4. So like in genus 0, there's of course the famous proof of mirror symmetry and some important step in Giventhals proof. Is to relate the J function of the quintic to the J function of P4. Because for the J function of P4, there's torus localization with the torus acting on P4, so it's much easier to handle and to compute. And this relation takes the form JQ equals J P4 O5. And this is the twisted, this one is the twisted theory. Of P4. And the basis of this is a key observation that can be written down as follows. So the virtual class of the moduli of stable maps to Q is equal to the class of moduli stable maps to P4 intersected with the Euler class of some vector bundle over the moduli of stable maps to P4. And I'm going to be referring as this as the quantum Lefschetz hyperplane principle. So this terminology is usually used for things that follow from this. So the correspondence between the J functions or the correspondence that this implies in quantum cohomology. So the terminology makes sense because the usual Lefschetz hyperplane principle relates the cohomology of P4 and Q, for example. So the quantum Lefschetz relates the quantum cohomology. But yeah, I'm just gonna call quantum Lefschetz this simplified thing. And in this form, so this is based on an observation of Kontsevich. So in 94, but in this form as this equality has been conjectured by Cox, Katz and Lee, and proved by Kim, Krush, and Pantev as a functoriality statement. Now, this relation doesn't hold in higher genus. In fact, in some cases, it doesn't even hold in genus 0 for orbifolds. I think it can be shown that there's no vector bundle for which a relationship like this can hold. But there are some ways to get around it. So in genus 1, one can recover some similar statement. So Lee and Zinger have some approach to computing Gromov-Witten invariants in genus 1. They use a similar statement. So a similar statement doesn't hold like written, but they consider, instead of the whole moduli of stable maps to P4, the closure of the main component. So the closure of the locus of stable maps to P4 coming from a smooth genus 1 curve. Then they resolve singularities on this. To obtain some reduced theory. And now for this reduced theory, there is a statement similar to what I called quantum Lefschetz, which allows to compute this reduced theory, and then the contributions from the other component on the moduli of stable maps can be computed from genus 0, so other contributions. Because the other components of the moduli space come from the genus 0 curves. So this is also important in the proof of genus 1, but it's hard to generalize this approach to higher genus, because from what I understand, it's hard to compute the contributions from Muller genus theories. There have been other approaches via the theory of quasi-maps. And in the theory of quasi-maps in genus 1, it turns out also that a similar relationship to what I called quantum Lefschetz holds. Now, so for higher genus, it's hard to generalize the story. And from what I know, there's two main approaches to the old genus computations. and one of them, so one whole genus approach is the theory of MSP fields or MSP fields by Chang, Junli, Wei-Pin, Melissa, and Huai-liang. And the basic setup, because this is where stable mass with p-fields arise, so I'm going to go into the general setup just very briefly, is, well, remember we called S this polynomial, defining Q. Now they consider C6 as C5 plus C with coordinates X and P. They consider this together with a sister action with weights 1, 1, 1, and -5. And with a superpotential W, which is a C-star equivariant and comes from S and is given by X and P mapped to Sx times P. So with this C-star equivariant superpotential, this descends to the stack quotient of C6 by C, which in turn has two different JT quotients, depending on the stability conditions. One is KP4, if the stability condition is the one that gets rid of the 0 in C5. So from C5, one obtains P4, and from the P coordinate, which is weight -5, one obtains of -5. So the total space of O -5 or P4. And the other JT quotient is C5 over Z5 if the stability condition gets rid of the 0 in C. So these two different JT quotients have some theories on them. This one as the Gromov-Witten theory of the quintic, and this one another theory of JRW theory. And what they try to do is relate these two theories, to relate these two theories. So their observation, their construction is that both theories can be seen as some Landau-Ginzburg theory associated to the data respectively of KP4 with how the superpotential descends to it, and C5 over Z5 with the superpotential that descends to it, and they construct virtual classes for these theories via cross-section localization. Which I'm also going to briefly talk about later. What they obtain on the left-hand side, this theory turns out and is proved by Chang and Li to be equal up to a sign to the Gromov-Witten theory of the quintic. And then they relate the two theories by constructing a master space. Which is a larger moduli space that contains both theories as different components of some bigger torus fixed locus. Okay, and they were able to do some.
Renata,
Yes.
one sec. You think you could keep the active part of the board a little lower? Because we mostly see we also mostly see the white screen, and then.
Yes, I'm sorry. Yeah, I do consider that. Yeah, and there's a main other approach by that's the log GLSM model by Chang, another one that Felix Yanda came to talk about and also has, okay. Anyway, that's the other approach that he talked about in the algebraic geometry seminar. So this is the part of the story that's interesting for me. Maybe I'll use orange. And this Landau-Ginzburg theory of KP4, it's what's called the theory of stable maps with P fields. So this is stable maps with P fields. So this is where it comes from. And my goal, or what I did, is to generalize this relationship to the different setup. Where instead of the quintic threefold MP4, I have Z, which is the vanishing locus of some section. X is some smooth projective variety. E is a rank R vector bundle. And S is some regular section, so intersects at zero section transversally. So Z is smooth, and it has some Gromov-Witten theory, and also there's some theory on stable maps with P fields on X determined by the bundle E and the section S, and I want to relate the two theories. Okay, so that's the end of a general overview. Now some main ingredients and some overview of the basics of the field, I guess. So we are all on the same page, also fixing notation. So technicalities. They called this section something else before, but okay. So we have the moduli of stable maps to some projective variety X, which is the moduli space of curves C with a map F to X. C itself as n mark points and is a pre-stable curve. And the push forward of the fundamental class of C should be some homology class beta. And I'm going to denote the moduli of stable maps just by curly X. I won't write all the subscripts G, N, and beta all the time because it's not terribly important to keep track of them for what I'm going to say. Everything goes through the same way regardless of genus and beta and so on. Now, this is of course proper DM stack. It's DM if we also ask for this data to be stable. So this is a proper DM stack, but it's not smooth. And as I guess briefly talked about in the genus 1 story, has different components. components in different dimensions. So one can get a nice theory by integrating against the usual fundamental class. Is not very useful. So one of the main tools of this is the virtual fundamental class. Which is a class in the expected dimension of this moduli space, and has been introduced and constructed by Lee and Tian and Baron and Fontecchi. Okay, to continue to fix notation and talk a little about this, since X is a fine moduli space, it comes with a universal family, so a universal curve with a projection and an evaluation map to X. And it lives over MGN free stable, which is the Artin stack of genus G pointed curves without requiring anything about stability. Just there are most nodal, and the mark points are distinct from the nodes. And the fiber, so it lives over this in the sense there is a forgettable morphism that forgets about the data of the map F. And the fiber of this is the possible maps F over this data. And living over this, one can define the virtual fundamental class in relation to the fundamental class of this Artin stack. Which is smooth and pure dimensional. And a key ingredient in constructing the virtual class, or rather actually something that's stronger than the virtual class, is VCF, virtual fundamental class, is determined by the data of a dual perfect obstruction theory. Shortened as POT, which roughly and locally is some complex of vector bundles such that H0 and H1 of this complex are quasi-coherent. And H0 is the tangent space of this morphism. I think when I write on the bottom of the screen, the pen is not so precise. So I'm going to scroll up a bit. And H1 is some obstruction space. To this morphism. And I'm going to denote H1 of this dual perfect obstruction theory by OB X2 and the sheaf of obstructions. And the perfect obstruction theory is usually given by some other definition in terms of a map to the cotangent complex. That's why it's usually written dualized. So like whether you consider the tangent shift or the cotangent shift to be the important object, but the conditions that are usually given are equivalent to this interpretation in terms of deformation theory. And given this data, so one should think of this of the perfect obstruction theory So the dual of this object as a cotangent complex, and so it sort of replaces the cotangent complex of the morphism from X to M with a two-term complex supported in -1, 0, and so makes the morphism into a sort of LCI morphism. And then one can construct a virtual pullback like the usual Gisin pullback for LCI morphisms from Fulton. So this data determines a virtual pullback. By a construction similar to the refined Gisin pullback. And this morphism, which depends on the obstruction theory, allows to pull back the fundamental class of M to some class in X of a specified dimension that depends on the dimension of M, which was pure, and the ranks of these two bundles. And this is the virtual class of X. So what is the usual perfect obstruction theory of Gromov-Witten theory? Well, studying this morphism that I wrote down before, one sees that the deformations of this data, of the additional data of giving a morphism fixed a curve. So the formations of a morphism where C and X are fixed are given by H0 of C F pullback of Tx and obstructions by H1. Okay, I'm sorry about the detail on this. Is that in the last part of the talk, I hope to talk about a little different perfect obstruction theories. I just wanted to introduce this a little bit. And this all can be then packaged into some global object. So the perfect obstruction theory just ends up being the derived push forward of the pullback by the evaluation map of Tx. Okay. Now, as well as X, we have curly Z, which I'm going to be defining as the union over all classes beta prime of Z, such that the push forward is B of the moduli of stable maps to Z with degree beta prime. Remember that Z is in X. Yeah, in the case Z is an hyperplane in X, then I can just take the class beta, but in general you need to be taking all this. And the inclusion gives a morphism from stable maps to Z to stable maps to X just by composing by the inclusion I. And now can relate the virtual fundamental class of Z to the virtual fundamental class on X. Yes, and since virtual fundamental classes look like the classical picture of Gisin pullback, this works the same way as classically. So classically, the way this works is say that Z, as I described before, this means that yeah, I'm making this maybe a little unnecessarily complicated. This means that there's some Cartesian diagram like this. X can be included in the vector bundle E, both by the 0 section and the section S. And there is this map gives a refined Gaussian pullback from cycle on X to cycles on Z. And the class of Z is just the Gaussian pullback of the class on X, which in particular implies that by SXS intersection formula, the pullback of the class of Z is the class of X intersected with the top Chern class of E. And so this is the classical picture, and the idea is that the quantized picture of the moduli space picture works the same way, but now we have these universal curves over the two moduli spaces. And some bundle over the universal curve on X. The problem is that this bundle is not a bundle over X, but it's a bundle over this universal curve. And okay, going to try to shorten this because maybe this will be too long. It turns out that the perfect obstruction theory of this morphism here, or the obstruction theory is not perfect in general, is given by something like this. So it lives in degrees 0, 2 in general, so it doesn't define a nice virtual pullback between the two spaces. But if R1 of this vanishes, then this is a perfect obstruction theory and defines this Gaussian pullback. And it turns out that if one pulls back the virtual class of X by this, ends up with the virtual class of Z. And this is by functoriality. It is a functorial statement, and it comes from some compatibility between the perfect obstruction theories on Z and X with this perfect obstruction theory of the relative morphism. And this in particular implies that the push forward of the virtual fundamental class on Z is equal to the top Chern class of the top Chern class of this bundle intersected with the fundamental class on X. Yeah, basically the nice thing now is that if R1 vanishes, then the push forward of this is actually a bundle on X, and Z is just the critical locus of a section of this bundle. And yeah. Okay, so that's the genus 0 picture, and this is proved by, as I mentioned, Kim, Crash, and Pantoff. And the virtual pullback terminology that allows to view this as just some analog of the Fulton picture is by Christina Manolac. Okay. So this fails if R1 pi lower star of this bundle does not vanish. which in the case of the quintic in P4 happens for all genus greater or equal than 1. Okay, so the fix or the replacement for this it comes from some other classical picture, or should come as an analogy of some other classical picture, which is, well, still with the same setup. We can view, instead of viewing Z as the vanishing locus of this section of the vector bundle E, we can construct on the total space of the dual vector bundle some superpotential W that comes from taking a fiber coordinate and taking a coordinate on the base and a coordinate on the fiber and mapping them to Sx paired with B. And now the degeneracy locus of this superpotential is Z, scheme theoretically, and one can construct a cohomology class a cohomology class associated to the degeneracy locus of this W that is supported on Z and turns out to be equal of the cohomology class of Z. Yeah, sorry, I'm just going to go a little more length here because this will come back later. So the degeneracy locus is where the differential vanishes. So assuming that we have some connection on E, so yeah, say we have some connection on E, then we can write the differential of the section S as a map from Tx to E. And we can write the vanishing locus of the superpotential as where this dW vanishes and this dW is a map like this that sends a horizontal tangent vector and a vertical tangent vector to this. Okay, so just differentiating. And it turns out to be somewhat important to have some nice expression for the differential of this superpotential. So we can just write it down with some nice expression locally or where here's a connection, but there should be some way to get around it that I'm going to be talking about. And the moduli space picture of this is to replace the total space of the dual of the vector bundle by what I'm going to introduce, another moduli space, that of stable maps with P fields, and the class of the degeneracy locus of W by co-section localized virtual class on this moduli space. Now, let me define these things. So this, it's usually denoted by MGN X beta P is moduli stable maps with p fields. And is a moduli space of stable maps to X together with a section of, well, the dual of E, because we want this to be an analog to the total space of the dual vector bundle. But for technical reasons, we tensor this by omega c, by the dualizing shape of the curve. And yeah, this is dual by surduality to exactly the space that wasn't vanishing before. So this was exactly the thing that was given problems in genus 0 and whose vanishing prevented us from having a nice global vector bundle that intersecting with the fundamental class of X, the fundamental class of Z. So this in general does not vanish because otherwise we're good. And the reason why we don't just take the moduli of stable maps to each check, but we also tensor this, from what I understand, has to do with the fact that in constructing the analogy of this formula, we use the pairing given by surduality rather than the dual pairing. So we need to put that omega c there. Now, this space, this moduli space comes with a perfect obstruction theory and a cosection of the obstruction shift. A cosection of the obstruction shift, okay. Maybe I should just mention that this moduli of stable maps with p fields lives over the moduli of stable maps to X. And it's just a cone. It's a affine space over it. And it's just a cone of R1 pi lower star. In keeping with the convention that the total space of a vector bundle is spec sim of the dual shift. So this is sort of like the Arshon convention, and this is a cone. So it's like the vector bundle E check over X. Okay, comes with a cosection. So the cosection is some map from the obstruction shift of XE to the structure shift of XE called sigma, which has some local expression, which has some explicit expression. That looks like the expression dW that I wrote down above. Okay, and has the generous locus. So just the locus where on XE, where this map here is not surjective, is just the moduli space Z inside of XE. Basically, yeah, it's because if, yeah, okay. So the generous locus is just this, where Z inside of XE is viewed as, well, stable maps to X with a P field, but we require the map to factor through Z, so to pull back, the pullback of S is 0 and P is 0. This is how it's included, and this is how one sees that the general locus of this formula is stable maps to Z. Okay, and given a moduli space, some threefold obstruction theory, and some cosaction, there is a construction by Chang and Li that to M some Deligne-Mumford stack with perfect obstruction theory E and cosaction from the obstruction sheaf. Associates some virtual fundamental class that it's supported on the general locus of the cosection sigma. And the push forward of this class. This won't be so important for this, and the push forward of this class by the inclusion of the general locus is the virtual fundamental class on the whole space, agrees with the virtual fundamental class on the whole space given by this perfect obstruction theory. Okay. Now so we have some perfect obstruction theory on the moduli of stable maps with P fields. That is supported in on Z, that is what we care about. And the main theorem, so this class here is well, before called the Landau-Ginzburg model of P4 with the superpotential W. And the main theorem is that the usual virtual fundamental class of stable maps to Z is equal up to a sign to this localized virtual fundamental class. And the sign is just the degree of the vector bundle over X plus R times 1 minus G, comes from Riemann-Roch. Okay, and this theorem has been proved in different forms and different setups by different people. So it's originally Z is just a quintic threefold and X is P4. And this is the original construction by Chang and Li, who introduced this moduli of stable maps with P fields. Then it's proved in the case of complete intersection by still Chang and differently, Moon and Li. Then it's proved again in the case of complete intersections in projective space. Then still in the case of complete intersection, I think it is in toric varieties by Kim and O, but this is sort of different because instead of virtual fundamental classes like this, it uses localized Chern characters. And then there's a proof by Shen, Yanda, and Webb. She came and gave a talk in Columbia about this in the general setup, where X is allowed to be a smooth projective variety. But yeah, this proof, I mean, proves this, of course, but doesn't really have an explicit expression for decosection. Sort of uses more machinery to define decosection, but just making it come from the superpotential. And yeah, I mean, I was working on this in a slightly different way. So, so I proved this in the context where, as I said, X is a projective variety and is any rank R vector bundle. Okay. My pen stopped working again, I'm sorry. Okay. I don't think there's, trying to remove the battery. Okay, now it's green. Okay, so I'm going to be talking about the idea of the proof. Quickly, and this is by the generation to the normal cone. Yeah, in the absence of a better understanding that can sort of mirror more closely the genus zero store, in which everything is some nice functorial statement, the proof is a little more hands-on. So the idea is that Z is this embedding into X, that taking the deformation space, the Fulton McPherson, I guess, the deformation state space can be degenerated to the embedding of Z as a zero section inside the total space of the normal bundle. So applying this idea to the moduli spaces, we can degenerate the moduli of stable maps with P fields, which were curves landing in X together with a section of the dual of E, to the P fields version of this, which turns out to be just the moduli space of curves with a map to Z, together with some field Q, which is a section of the pullback of E, and some field P, which is still a P field. Okay, and now there is, now this space is a cone over our modular space Z, and has a perfect obstruction theory relative to Z, which of which the obstruction sheaf just looks like the obstruction to the form in the data of Q and the data of P. So Q and P are just sections of some vector bundle. They can be deformed just by adding another section of this vector bundle, and the obstructions to the form in the data of P and Q just leaving H1 of the vector bundles. So locally, the obstruction theory looks like this. I guess over some point C, F, Q, and P. And the cosection is now given by just by Q dot P dot maps to Q dot P plus P dot Q, just product rule. And yeah, as this nice expression. So clearly the vanishing locus of this, now the pairing here is her duality. And that's why we need to replace the dual of the vector bundle with the dual of the vector bundle tensor by omega c. So the degeneracy locus. So this cosection here is what the original cosection is the deformation of the original cosection. Sigma, and by deformation invariance, or some form of deformation invariance of virtual fundamental classes with cosections that say that if you deform the space and deform the obstruction theory and deform the cosection, then the fundamental classes are the same. We have that the fundamental class of the cosection localized fundamental class of this deformation is equal to the original one. Now, this is supported on the degeneracy locus of this cosection, which is clearly Z because P and Q vanish. And we can relate this cosection localized virtual fundamental class to the original virtual fundamental class on Z by cosection localized torus localization by making C star act on the fibers of the bundle N with weight 1 and on the duals with weight -1. Then the cosection is torus equivariant, which is the condition for torus localization to apply to cosection localized classes. And this proves that this class, since they have the same support, it proves that this class is the same as this class up to the sign that comes from the localization. So that's where the sign comes from. Okay, any questions before I move to the next part? No, okay. To understand the moduli of stable maps with B fields more concretely, and to give a concrete formula for the cosection. Without a connection. It's nice to work relative to BAN, G, and DR instead of my curly M from before. This here is the moduli space of prestable curves, prestable M-pointed curves. Together with V, vector bundle of rank R and degree D, where we fix D to be equal to the degree of the vector bundle on X. Now, we had that fixing X, we have the moduli space of stable maps to X and a forgettable morphism that just remembers the domain. If we fix the additional data of the pair of X and the vector bundle E, then we have some new forgetful morphism from the moduli space of stable maps to X to this bungee, which I'm just going to be calling curly G. And this is given by remembering the domain curve and the data of what the vector bundle E pulls back to. So we forget the map, but we just remember about the pullback of the vector bundle. And now it's nice to work relative to this. And to work relative to this, we need to give different, we need to figure out what the perfect obstruction theory of this morphism should be in a way that agrees with the perfect obstruction theory of this morphism. That's the one usually used to build the virtual fundamental class. So this perfect obstruction theory of X relative to B has to do with the problem of, well, fixing a vector bundle on my curve and fixing the vector bundle on X. Let's say that we have some morphism F from C to X such that V is the pullback of V. And the problem is the formations of F that fix the fact, fix the pullback of the vector bundle E. And this problem is controlled by some vector bundle AE, which sits in some extension, which is defined by the IT extension, which is simply some short exact sequence that looks like this. I'm going to make this more concrete in a second, which is some short exact sequence like this that extends the tangent space dx of x. And it turns out that H0 of the sections of this AE are automorphisms of the pair of a smooth variety together with a vector bundle, and H1 are deformations of this pair. And the nice thing is that taking something, taking some element of the automorphisms of this pair and mapping it down to this, one just remembers the automorphism of the base of this pair, which is an element of H0 Tx, and if this is 0, then the automorphisms leaves just an automorphism of the bundle. Anyway, using this, this classical fact from deformation theory, one obtains that H0 of the pullback of this bundle is the deformations of this data, and H1 is obstructions. So this all fits in nicely and gets packaged in a relative perfect obstruction theory given by this that defines a virtual fundamental class on X, and this agrees with the usual virtual fundamental class defined where we consider the perfect obstruction theory that had to do with forgetting the map and mapping down to the moduli space of pre-stable curves. And something nice about this, so a nice way to get this Atiyah bundle explicitly is to consider the fact that this problem of giving a map from C to X that pulls back the bundle E to V is the same as the problem of giving a map F, which is Geller equivariant between the frame bundles. Of V and E, or the associated Geller torsors. And then the deformation theory of this has to do with the tangent space of PE quotiented by Geller, say, and this turns out to be the same as this. Yeah, the idea is just that there's a connection on principal bundles. There's always a connection. So the tangent space splits, and that's how this works. And that's how Atiyah constructed this extension. And basically, this extension is this here is split if and only if there is a connection on our bundle. So this connection here, this extension here measures measures the failure of our bundle to have a connection. And I guess the point of this is, for example, on the original P4, if we pick E to be line bundle OK for any K, we have that A of OK is isomorphic to A of O1 for any K, and the short exact sequence above is just the Euler sequence. I mean, this works for not just P4, I guess, any protracted space. And so the perfect obstruction theory of maps to P4 of degree D with respect to beta is just given by O1 plus 5, which is well known and corresponds, so for K equals 1 corresponds to the fact that given giving a map from C to P4 together with some very ample bundle on C, so together with a choice of this, it's the same as giving very ample line bundle on C and some sections. plus stability conditions that are actually not very important for obstruction theories, and yeah, can be varied by like. So that is the basic, and the natural way to generalize this, I guess, would be to fix some very ample line bundle or some vector bundle of which the sections give embeddings on the variety X, and then work with that perfect obstruction theory. But that doesn't really carry any information about the bundle E, and I wanted to carry some information about the bundle E. And so just using the bundle E, one can give this relative perfect obstruction theory. And the nice thing about it, so useful thing about it, is that on this vector bundle AE, we always have a way to differentiate the cosection. And this way of differentiating the cosection, if I mentioned the short exact sequence above is split, is just a way of differentiating the cosection as if we had a connection. And if that's not split, just gives me a way to differentiate S and understand the cosection as actually just the differential of the superpotential. And this map here just comes from the fact that the section S defines some map from PE, the frame bundle of E, to CR, which is Geller equivariant. And yeah, when I unpacked these definitions, this gives this map. And this delta S also has some deformation theoretic meaning, and the kernel of this delta S has to do with sections that extend to the deformations of the pair X and E when one deforms the pair X and E. But the main point is that one can use this delta S to define the cosection sigma on the modular space of stable maps with P fields. And yeah, this is sort of like a long story about one detail, because the original proof for P4 of this stable maps with P field story uses this perfect obstruction theory on the modular stable maps to P4, that then extends a perfect obstruction theory to the moduli of P fields to give this cosection with a nice coordinate expression. And I just wanted to generalize this story without having to pick a very ample line bundle on X. So yeah, this is just something that I found interesting in this. And yeah, I think this is all that I'm going to say. I'm a little early, but I think that's better, possibly. Any questions? I think you're muted.
I'm muted. Yeah, I was trying to encourage people to ask questions.
Oh, I didn't see that. Is there a shot?
Maybe this question is silly because I don't know if these situations come up in Gromov-Witten theory, but when you want to construct an obstruction theory, you kind of extend this case of the zero section of a vector bundle to instead look at the degeneracy locus of a map between two different vector bundles. And so you where this map has minimal rank. Do these methods give you some kind of theory of P fields or some kind of quantum Lefschetz theorem in that setup?
I don't think there's a construction of cosection localized virtual classes that instead of the cosection to a rank 1 thing takes a cosection to a higher rank thing. And it's because they sort of lied in the classical story, saying that the cosection localized virtual class was like an analog of the degeneracy locus construction classically. It's really not. it's really not really, and I'm trying to understand what it is an analog of classically, but no, as far as I know, there's no construction of higher degeneracy loci.
I see.
Sorry.
No. Okay.
Oh well, if there's no more questions, then we continue next week. Thank you, Renata. That was really good. Please send me if you don't mind this your notes and your videos will be posted on the web page. Please send me the notes.
Okay. Thank you.
All right. Thank you, Renata again. Thanks
Bye.
everybody.
Bye.